Okay, in this chapter, we'll study fluids and pressure. Um, Pressure in the human body in various systems is a good indication of good health or bad or disease. So, this is an important chapter. Pressure is defined as force per unit area. Okay, and so the units in which pressure is measured is force is measured in newtons, that's measured in meters square, and the units for pressure are Newton per meter square, which is named a Pascal after Mr. Pascal. So here are some pressures. So this is in SI units. Okay, 1 atmosphere. Where is 1 atmosphere? 1 atmosphere is 10 to the power 5 pascals. Okay, so roughly 1.013 times 10 to the 5 pascal. So we'll say 10 to the 5 pascals. 1 atmosphere in pounds per square inch is given by about 15 pounds per square inch. Okay. The pressure in the medical field is measured in millimeter of mercury, and it's 76 centimeters of mercury. 1 atmosphere is 76 centimeters of mercury, or that's 760 millimeter of mercury. Okay, so here are various units that you will use. Okay, now a record player needle exerts pressure on a record. So here are some examples where you experience water near the bottom of a swimming pool exerts noticeable pressure on a swimmer's eardrums. So you'll feel, and if your middle ear pressure doesn't equalize, it'll hurt. Okay, and atmospheric pressure changes with weather conditions. Anyways, here's pressure. Okay, so let me show you a little app that shows you how a gas exerts pressure. Right, so here's a gas, and see, this is quite a high pressure. This is 22 atmospheres. Okay, and the way the gas is, so what this pressure means is, okay, so let me change this pressure. Okay, so I'll change this to about 20 atmospheres. Okay, there you go. So that's about 20 atmospheres. I changed it to 20 atmospheres. So what 20 atmosphere means is 1 atmosphere is 15 pounds per square inch. So 15 times 20 is 300 pounds per square inch. So the gas molecules bouncing off these boxes are exerting a force of 300 pounds per square inch of the box. So that's what that number means. Okay, and that's a very large force. Okay, so so you can think of pressure. So when water exerts pressure at the bottom of a glass or a swimming pool, it's the water molecules bouncing off the walls or the surface that are exerting the force. Okay. All right. So pressure is force per unit area. Okay. So for instance, when this person applies a force there, and you apply an equal force with a needle, the needle tip has a much smaller area, and so the pressure, if you apply the same force on a much smaller area, the pressure is much higher. And given a high enough pressure, you can break your skin. Okay, so if you apply a certain force with a needle using the same force, you just don't feel it. The needle penetrates your skin. Okay, so pressure is inversely proportional to the area. Okay, fluids, that's liquids and gases, as well as solids, can exert pressure. So, okay. So again, pressure, 1 atmosphere is about 10 to the power 5 Newton meter square. Okay, so here are two different useful ways of seeing pressure. You already saw this example. The pressure is the force exerted by the fluid, and that's the force exerted is by the molecules bouncing off the walls. Okay. Here's another useful way of thinking of pressure. This is atmospheric pressure, which is 10 to the power of 5 Newton per meter square. And 1 meter square is there is a meter square. 1 meter square is a little over 1 yard square. Okay, and so this column of air all the way to space weighs 10 to the power 5 newtons. Okay, and here's a way to think about it. 10 to the power 5 newtons. The weight of something is the mass times gravity, and g is about 10 meters per second square. So this number divided by 10 would be 10 to the 4, which is about 10,000 kg. Okay, so what that means is this column of air all the way to space weighs about 10,000 kg, which is roughly the weight of a school bus. Okay, so pressure is also the weight of that column. Okay, again, you want to remember this number. Atmospheric pressure is 10 to the power 5 pascals and 760 millimeters of mercury and 15 pounds per square inch. Okay, so those are some of the numbers that will be good to remember. So here's a little problem showing you how enormous the atmospheric pressure is. So the atmospheric pressure exerts a force. So pressure times area exerts, that would be the force on this wall. Okay, so calculate the force in Newton exerted by atmosphere on one side of a wall of area 10 meters square. Okay, so this wall is 10 meters square, and the force on this wall, so if you force would be pressure times area, and this works out to 1,000,000 newtons. Okay, 1,000,000 newtons is again, that force is, if you divide that by g is 10, so the mass would work out to 100,000 kgs, and that's the weight, that's the mass of 10 buses. So the atmosphere is exerting a force of equal to the weight of 10 school buses. And the reason this wall doesn't collapse, of course, is because there's an equal and opposite force on the other side. Okay. So this illustrates how large the atmospheric the pressure is. Okay. Stationary fluids always exert forces perpendicular to the surface. So the fluids always exert a pressure that's perpendicular to the surface. No matter what the surface is, the force is always perpendicular to the surface. Okay, so you saw that atoms bouncing off the wall exert a force on the wall, and that's how pressure is exerted. So gas in a container exerts pressure on the walls. This pressure is caused by collisions of the molecules with the walls. Many billions of molecules strike the wall every second and thereby exert a nearly constant average force. Okay. Here's how, for an ideal gas, here's how pressure, volume, and temperature of the gas are related. So this is the pressure the gas is exerting. That's the volume of the gas. That's the number of moles of gas. That's the gas constant. And that's the temperature in Kelvin scale. Okay, so this is the ideal gas law. This is the ideal gas law. And this will be useful for us. Like we said, all fluids exert pressure. Okay, so the pressure is at this depth in a swimming pool. So the pressure would be, remember, another way to think of the pressure is, it's the weight of this column of air all the way to space. So there you would have atmospheric pressure. And so if you want to calculate the pressure at this point, then that is plus the weight of this liquid. Okay, so the pressure at this point is the atmospheric pressure plus the weight of this column of liquid. And that's what this is. This is atmospheric pressure, and this is the pressure of this column of liquid. So underwater, as you go deeper and deeper, the pressure increases. As H increases, pressure increases. In fact, if you go down 33 feet or 10 meters, this term, so this is the density of water, which is 1,000 kg per meter cube. So the density of water is 1,000 kg per meter cube, and this fellow is 10 meters per second square roughly, and that's, if you go down 10 meters, that'll equal 1 atmospheric pressure. Okay, so if you're swimming under, if you're diving and you're at a depth of 33 feet, then you have to breathe air at 2 atmospheres. If you're at 66 feet, you'd have to breathe air at 3 atmospheres, because this will become 2 atmospheres and the total pressure will be 3 atmospheres. So this expression gives you pressure at a depth. And this will be important to us. Okay, now in the medical field, a lot of times pressure, so this is called absolute pressure. This is called absolute pressure. Okay, and a lot of times we talk absolute pressure minus atmospheric pressure. So a lot of your instruments measure this, and this is called gauge pressure. Okay, so when you give blood pressure, when you're quoting blood pressure, it's gauge pressure that you're quoting, and it's that's so just remember that that's what we quote in all situations. Okay, so absolute pressure is the total pressure, and gauge pressure is absolute pressure minus atmospheric pressure. So gauge pressure is atmospheric pressure absolute pressure minus atmospheric pressure. Okay, so we shall use the convention that all pressures are gauge pressures unless otherwise specified. So in most medical applications, you're always quoting gauge pressure. Okay, so absolute pressure is the total pressure, and gauge pressure is total pressure minus atmospheric pressure. All right, so now here's the situation. So if you have a tube and you want a fluid to flow, if you want the fluid to flow here, this side has to be higher pressure and this side has to be lower pressure. So fluid flows from a higher pressure to lower pressure. All right, so here's an IV system, and so if you want this fluid to flow into the veins of this patient, the blood vessels have a pressure in them. So the pressure due to this column should be greater than the blood pressure for the fluid to flow into the patient. Okay, so and as you saw that to increase the pressure at this point, all you have to do is raise the fluid. Okay, so if the IV fluid is not flowing in, that means the pressure due to this column is not larger than the blood pressure, and you just have to raise it. So, and it has to be greater than the systolic pressure. Okay, so now also, so now the manifestation of how pressure depends only on depth and density is found in the intravenous system administration of fluid. Okay, so what this line is saying is, we're trying to say is, it doesn't matter how the tube is shaped, the pressure depends only on this height. Okay, so what you're trying to do is, so the gauge pressure here is the density of this intravenous fluid, which is essentially the density of water. Okay, so the pressure is the density of the fluid times this height. Okay, so what you want is this pressure to be greater than your systolic pressure. Okay, and so the fluid will flow into the patient. The pressure due to the IV fluids at the entrance of the needle is proportional to the height of the surface above the needle. It's proportional to this height. Okay, the path taken is irrelevant, whether the tube is like this or like that, it doesn't matter. the applied pressure can be adjusted by raising or lowering the IV bottle relative to the entry point. So here's how an eyedropper works. Okay, so you put the dropper underneath the liquid surface, you squeeze the dropper and you're forcing air out, and once you let go of the squeezer, the bulb, now there's partial vacuum created, and remember, fluid flows from a higher pressure to a lower pressure. Okay, so there's low pressure in there and there's higher atmospheric pressure, which will force the liquid in. Okay, and once the liquid rises to the point such that this pressure plus this pressure is equal to 1 atmospheric pressure. Okay, so it rises to that point. Okay. All right. Now we'll study Pascal's law. Okay. So if you have an enclosed fluid, what Mr. Pascal discovered was, if you increase the pressure at any point in the fluid, let's say you press down on it and increase the pressure at this point by half an atmosphere, at every point in the fluid, the pressure will increase by half an atmosphere. Okay, so that's what, so let's say you increase the pressure at this point by this much by applying a force F1 over A1. A1 is the area of this piston. That increase in pressure is transmitted everywhere in the fluid, so the pressure at that point also increases by the same amount. So F2 divided by A2 is equal to that. Okay, so what this device does is it's a force multiplier. Now let's solve for F2. F2 is A2 over A1 times F1. So let's say if this area is 20 times larger than this area, then F2, the output force, will be 20 times the input force. So this is a force multiplier, and you'll see the application in a second. Okay. So here's an application. So for instance, in the a dentist chair. Okay. So here's this piston has a diameter of 1 centimeter, and this piston has a diameter of 5 centimeters. So the radius of this guy is 5 times greater than that. So the area of this guy, area A2, is, the radius is 5 times greater, since area of a circle is pi r square. And if the radius is 5 times greater, this area is 25 times greater. So A2 over A1 is 25 times. So like we said, F2 will be 25 times greater than F1. Okay, so in a dentist office, this is where the patient sits. The patient's chair is above this, and the dentist pumps this with a pedal and is able to lift up the patient. Okay, and that's what this problem shows you. Okay, so this is 120 kg patient and chair. The mass of the patient and chair is 120 kgs, and that's in newtons. That's about 1200 newtons. And the dentist is able to apply a force of 50 newtons and lift a patient in chair of 1200 newtons. Okay, so that's roughly 25 times. Okay, this force, now let me convert that to pounds. If you divide that by 10, that's about 5 kgs, and each kg is 1 kg is, each kg is about 2.2 pounds. Okay, so this is roughly 11 pounds. With a force of 11 pounds, he's able to lift 25 times that. So 1110, 260 pounds. With the force of 11 pounds, he's able to lift 260 pounds. Okay, so that's Pascal's principle. Again, the Pascal's principle says if into an enclosed fluid, if you increase the pressure at any point in the fluid, that pressure is transmitted undiminished. A change in pressure applied to an enclosed incompressible fluid is transmitted undiminished to every other point in the fluid. Okay. All right, so when we measure blood pressure, okay, so the heart is pumping blood and we want to measure the pressure. So what you do is you put a cuff right at the heart level, okay, and then start squeezing with a bulb. Okay. So the heart is pumping blood and the blood is in pressure. So now if you apply a pressure greater than the pressure that the heart is applying, the blood vessel will collapse if the external pressure is higher, and the blood vessel will collapse and the blood flow will stop. Okay, and that's what you're doing. So what you do is you apply high pressure, make the blood stop, and then slowly start reducing the pressure, and listen to when the blood first starts flowing. By the way, so the cuff has to be at heart level. Okay. So when the applied pressure exceeds the heart's maximum output pressure, the artery collapses. The person making the measurement slowly releases air from the cuff, lowering its pressure, and listens for the flow to resume. When the pressure in the cuff becomes lower than the maximum heart output, blood will start flowing, and this is called the systolic pressure. Okay. So you're listening for the heart and the blood flow to restart, and that's the systolic pressure. Okay. And the diastolic pressure is the minimum pressure that that the blood is flowing at, and the diastolic pressure is the minimum pressure the circulatory system experiences and can be detected as a change in the sound of blood flow through the partially restricted. Okay, so you keep reducing the pressure, and as the artery goes back to its full size, when this pressure is decreased below the minimum pressure, the flow will sound different. So when it's unrestricted, the flow will be smoother and there won't be any sound, okay? Or the sound will be of a different nature. Okay. So the systolic pressure is the maximum pressure that the heart is pumping out, and the diastolic pressure is the minimum pressure. All right. So in the next chapter, you'll learn about why we measure this spinal column pressure. So there's a cerebrospinal fluid that surrounds your brain and flows through the spinal column, and you want to measure that pressure. And to measure that pressure, you use a syringe with a saline solution in it. Okay, and if you want to measure the pressure at that point, the patient has to be standing, and the syringe has to be horizontal. If it's like that, you measure too low pressure. If you point the syringe like that, you'll measure you'll measure lower pressure, and if it's like this, you'll measure a higher pressure. So that's where the gauge is. Okay, so this has to be horizontal. A manometer is a device that measures gauge pressure. So manometer, so this point is going to where you're measuring the pressure. So for instance, if that goes to the cuff, that's where the pressure is measured, and this is open to the atmosphere. And this height, so this height would correspond to the gauge pressure. Okay, so here's a manometer that a doctor uses. Okay, so they're a blood pressure measuring device, and they're measuring the gauge pressure. Okay, a single tube manometer filled with mercury is commonly used in blood pressure measurements. So typical blood pressure measurements range, again, these are gauge pressures from 8 to 300 millimeters of mercury. Remember, 1 atmosphere is 760 millimeter of mercury. So healthy blood pressure is 120 over 80 millimeters of mercury. So 120 is roughly, so 10% of that atmospheric pressure is about 76 millimeter of mercury. So about 15% atmosphere and about 10% of atmosphere. So a healthy gauge blood pressure is 10 to 15% of atmospheric pressure. Okay. A barometer, so a manometer measures gauge pressure, a barometer actually measures the actual pressure. So again, here's a mercury barometer, and what you can do is take a tube and fill it with mercury, and take a tube, fill it with mercury, and then insert it in a bath of mercury. Okay, put your thumb across it and invert it in a bath of mercury, and the mercury will drop, and this will be perfect vacuum, and this column of mercury is balancing a column of air all the way to space. Okay, so that column of mercury is balancing this column of air all the way to space, and this weight is equal to this weight, and that's atmospheric pressure. And so under normal circumstances, this will be 76 centimeters of mercury or 760 millimeters of mercury. Okay. So 1 atmosphere would be 0.76 meters, 76 centimeters, or 760 millimeters. Okay. So again, 0.7 meters, 76 meters, 76 centimeters, or 760 millimeters of HD. That's 1 atmosphere. Atmospheric pressure varies with altitude and conditions. So you go higher up, you got less and less atmosphere sitting on top of you. So the atmospheric pressure lowers. All right, so here's an example of the idea of pressure. Pressure is force divided by area, and so force is pressure times area. Okay, so in patients that have aneurysms, okay, so an aneurysm is a ballooning of your blood vessel, okay, and you can see that will show you that if your blood pressure is high, the force on this thing can be large enough where you can bust it. So it's like a balloon, and the forces, the walls are weakened to begin with, and if your blood pressure goes too high, the forces applied on it can be large and it can bust open. So calculate the maximum force in newtons exerted by the blood on an aneurysm ballooning in the aorta, given the maximum blood pressure is 140 millimeter of mercury, so slightly high pressure. The area of the aneurysm is 25 centimeters square. Okay, so the surface area of a balloon is given by 4 pi r squared, where r is the radius. Okay, and so if you take that and divide by 4 pi and so on, essentially this aneurysm is about an inch across. Okay, so let's calculate the force on an aneurysm, and that's an inch across with the pressure of 140 millimeters of mercury. So this problem goes through all the calculation, and the force works out to about 50 newtons. Okay, and again, like I said, this is, we calculated a similar number in the dentist chair problem, and this is about 12 pounds. So there's 12 pounds of force acting on that aneurysm, and total of 12 pounds of force, and that aneurysm can burst. Okay, so this is a large force for the blood vessel to withstand, and there's considerable risk that the aneurysm will burst. So do your best so the patient should keep their blood pressure low so that the aneurysm doesn't burst. All right, so now we'll talk about buoyant force. If you immerse an object in a fluid, it will feel an upward force. Okay, and that happens because, see, as you go deeper in a fluid, the pressure increases. So at a deeper point, the pressure is higher than this, and so there's a net force, upward force. So the force at the bottom is higher than the force at the top. So there's a net upward force acting on the object, and that's the buoyant force. Okay. So if you have a piece of wood, the buoyant force is greater than the weight of the wood, and so the wood will rise up. And if you have a stone, the weight of the stone is greater than the weight of the and then the buoyant force of the stone sinks. Okay. And if the buoyant force is exactly equal to the weight of the object, and that'll happen when the density of the object is equal to the density of the fluid, it can remain suspended in the fluid. Buoyant force is the result of increasing pressure with depth. Okay. Mr. Archimedes figured out exactly how large this buoyant force is. This buoyant force is equal to the weight of the fluid that is displayed. So this object displays that much fluid, and the weight of that fluid is equal to the weight buoyant force. So the buoyant force is equal to the weight of the displaced fluid, and it's given by the density of the fluid times the volume of the fluid displaced times acceleration due to gravity. So underwater, your apparent weight will be your actual weight minus the buoyant force. Okay. So in fact, if you stand in a pool, since density of people are a person is almost equal to the density of water, if you weigh yourself underwater, you'll essentially be weightless. Okay. So your apparent weight will be zero or close to zero. All right, when does an object float? So here's an ice cube floating. An object will float when its density is less than the density of the fluid. Okay. So for instance, in the Dead Sea, the density of the water in Dead Sea is greater than the density of all people. So every person will float. And you might have seen pictures of that. Okay. Anyway. An object will float when its density is less than the density of the fluid. So, and the fraction that is underwater. So here's an iceberg. The density of the ice is 90% that of seawater. So 90% of the iceberg is underwater. Okay, so this formula tells you that density of the object divided by density of fluid, it's equal to the volume displaced, meaning the volume underwater, divided with the volume of the object. Since this is 90%, 90% of the object is underwater. Yeah. So about 89% of the iceberg is below the water surface. All right, so we'll come to a very important application for biological sciences, fluid flow. Okay, now if you want to make a fluid flow, like we've already mentioned, you have to have a higher pressure here and a lower pressure there. Okay, and then you can make the fluid flow. Okay, flow rate is how many gallons are flowing per minute, or however you want to do it, measure it. Okay, and that's denoted by Q, and that's equal to pressure difference divided by the resistance. Okay, so pressure difference is high pressure minus low pressure, or in some diagrams it's also denoted as P2 and P1, divided by the resistance that the fluid is providing. Okay, so for instance, if you're trying to pump honey with the same pressure difference versus water, honey has greater resistance, and there'll be other factors that go into that, and we'll come to that. The resistance depends on the viscosity. That's honey has greater viscosity than water. It also depends on the length of the tube. L is the length of the tube. and it depends on the radius of the tube. Wider the tube, greater the radius. Okay, so it depends on the radius of the tube. Greater the radius, smaller the resistance. So it's easier to pump the fluid through a wider tube, and that makes sense. So pressure push fluid from a high pressure region to a lower pressure regions. Flow rate is directly proportional to the pressure difference between the two regions and inversely proportional to the resistance. Greater the resistance, lower the flow, and higher the pressure difference, higher the flow rate. Okay, so we'll come to this equation often enough, so you might want to memorize this again. Flow rate is pressure difference divided by resistance. So French scientist PHY was interested in the physics of blood circulation. He found that for laminar flow, we'll define laminar flow in a second, of an incompressible fluid, resistance depends on three things: the length of the tube, its radius, and viscosity. Okay, so viscosity is friction in the fluid, so the resistance is proportional to viscosity. Again, honey has higher viscosity than water, length of the tube, and inversely proportional to the radius to the power 4. This will be very important. So we'll see that resistance. So for instance, when you exercise and you want to increase flow rate, one way to decrease the resistance, so if you want to increase flow rate to skeletal muscles when you're running, okay, if you increase the pressure difference, your heart is having to work harder. But an easier thing to do is decrease resistance, and you can decrease resistance by increasing the radius of the blood vessels supplied to the skeletal muscles. You increase the radius and the resistance decreases, blood flow increases. So we see that the resistance is inversely proportional to the radius raised to the 4th power. The resistance and therefore the flow rate is extremely sensitive to the radius of the tube. In fact, the easiest way to adjust flow is to change the radius of a tube. The body's circulatory system does this by constricting and dilating blood vessels, often in specific organs. Okay, so that's how the body controls. That's one of the easiest ways how the body controls flow rates. So again, here's the flow rate, which is the pressure difference divided by the resistance. And resistance for here is laminar flow. Laminar flow is when the fluid is flowing in a nice layered fashion. Okay. And so for instance, this is turbulent flow. And with turbulent flow, the resistance is much higher. So your body will have to work much harder to make blood flow. And when the flow is nice and smooth and in layers, this is a laminar flow, and the resistance is lower, and you don't have to work as hard to pump this blood. All right, so flow rate is pressure difference. Here is the pressure difference between two ends of the tube and divided by the resistance. And you saw PHY gave you an expression for the resistance, and if you put this expression in there is the flow rate. There's the pressure difference between the ends of the pipe, pi r to the power 4, and 8 eta is the viscosity of the fluid, and L is the length. So if this was a blood vessel and you want to increase the flow rate, the pressure difference is maintained by the heart. Well, you can make the heart work harder, or just dilate the blood vessel. If you dilate the blood vessel, you increase R, and you can increase the flow rate. So we'll see an example soon. Okay, so when a person eats a large meal, the blood flow in the digestive system is increased by dilating blood vessels supplying the system. So let's say you want to increase the flow rate from 1 liter a minute to 5 liters a minute. So you increase the flow rate by a factor of 5. Okay, so there is the expression for the flow rate. You're going to keep the pressure difference the same. All you're going to do is dilate the blood vessels. And so this problem goes through the calculation, and all you have to do is dilate the blood vessels by 50%. You dilate the blood vessels by 50% and you get a 500% increase in flow rate. Okay, so that's the easiest way to control flow rate. So we see that if the radius is increased to 1.5 times of 1.5 of its original size, the flow rate will be 5 times the original value. So 500% increase in flow rate is accomplished by 50% increase in the radius of the blood vessel. Okay. So that's the mechanism the body uses most often. Okay. So when you do strenuous exercise, you want to increase flow rate to, let's say, your skeletal muscles, and you just dilate the blood vessels and increase the flow rate. So during strenuous exercise, to increase flow rate, the human body does both. In the circulatory system, the blood pressure increases, increases also slightly, and the major blood supplying arteries dilate. Okay, so they increase that and decrease the resistance by dilating the blood vessels. All right, so if you have an IV system, there's the flow rate again, and okay, there's the pressure difference dependent on the height. And if you want to decrease the flow rate, what you can do is you can increase the resistance. And as you saw, increasing the resistance is, you can increase the resistance by decreasing the radius of the tube. So if you put a clamp, you you increase the resistance quite a bit. Okay, so adding a clamp will decrease the flow rate. Okay. So we'll talk about turbulent flow now. Okay, so this is laminar flow. When a fluid is flowing in, when the flow is laminar, then for a given flow rate, the pressure difference has to be low. If the fluid becomes turbulent, then you have to work harder for the same flow rate. So as long as so if you want to save energy, what you want is laminar flow. Okay, now in the body, many times the flow does become turbulent, and we'll see under what circumstances it becomes turbulent. So turbulence is characterized by eddies and swirls in the fluid stream. So you have eddies and swirls. Resistance for turbulent flow is significantly larger. So resistance is larger, and for a given pressure difference, the flow rate drops. Okay, so now for laminar flow, you saw the resistance. The formula for a resistance was 8 eta L divided by 4 pi r to the power 4. Let's make sure. Yep. Pi r to the power 4. Again, there's no 4 there. Okay. So this formula applies when the flow is laminar. Okay. But this formula does not apply when the flow is turbulent. But this formula applies for both cases. Okay. Anyway, for turbulent flow, the resistance is much higher than given by this formula. Okay, so when the flow is turbulent, resistance is high, and for a given pressure, the flow rate is reduced. Turbulence has many causes. Sharp bends and partial obstructions, particularly those with irregular shapes, can cause eddies to form. So a plaque deposit in a blood vessels can cause turbulent flow. It is often possible to hear turbulent flow because of the sounds made by the eddies. So when you hear water running somewhere in your home, the sound is turbulence. usually in the valves. Heart murmur are sounds produced by turbulent blood flow. So heart murmur is produced by turbulent blood flow through a defective heart valve or hole between heart chambers. Okay, so an aneurysm, ballooning of the artery, can also cause audible turbulence because of its shape. So defective heart valves, holes in the heart chamber, aneurysms, they can all cause turbulence. Turbulent flow always presents more resistance than laminar flow. Okay, again, so flow rate is difference in pressure divided by resistance, and soon as turbulence sets in, resistance increases and your flow rate drops. So if you want to maintain flow rate, you have to increase the pressure difference, and you're working harder. And higher pressures will cause problems elsewhere. Okay, and we'll see that in the next chapter. Turbulent flow always presents more resistance than laminar flow. The onset of turbulence reduces flow rate if the pressure difference is constant. So if this is constant, higher resistance decreases the flow rate. In the case of an aneurysm, if the body wants to maintain the same flow rate, it tries to increase the pressure. And in the case of an aneurysm, the body may respond by increasing blood pressure to maintain normal flow rate. Unfortunately, increased blood pressure only worsens the aneurysm. Okay. So in an aneurysm, because turbulence sets in, resistance increases, and when the body tries to maintain the flow rate, increasing the pressure, the aneurysm might burst. Okay. Modern cars are designed to cause minimal turbulence to avoid extra resistance and increase fuel consumption. Aircraft, ships, and submarines are similarly designed, and the shape of the fastest birds and sea life are such as to create very little turbulence. Right? So that's what we mean by an aerodynamic shape. We want to minimize turbulence. So again, here's laminar flow, here's the transitional stage, and here's turbulent flow. So turbulence is also caused by large fluid speeds. So about critical speeds, friction between the fluid and the walls of the tubes starts eddies. Okay, and so commercial aircrafts are flown at less than top speed for this reason. So one reason supersonic aircraft consume inordinate amount of fuel is that at those speeds it's extremely difficult to avoid turbulence. Okay. So essentially the punchline is turbulence costs you money and it costs you trouble. So you want to try and avoid it at all costs. In small blood vessels, especially capillaries, interaction of the cells with the vessel walls causes turbulence. In large vessels, blood flow is approximately laminar, and Pauz's law applies quite well. So you saw that for laminar flow, the expression for resistance was 8 eta L divided by pi r to the power 4. But for turbulent flow, you don't have any formula like this. Okay. Resistance during turbulent flow depends on the radius and length of the tube, just like that. The viscosity of the fluid and other factors such as speed of the object moving through the fluid and stuff, and other factors. Okay. So for instance, in your cars, so if you drive at 55 miles an hour or lower, then there's no turbulence. So fuel consumption in cars driving at steady speed on level ground is due entirely to work against friction. So as long as fuel consumption does not greatly depend on the speed of the car, up to 55 miles an hour, Above 55 miles an hour or 90 kilometers an hour, the floor becomes noticeably turbulent and resistance increases. In addition, greater the speed above where the flow becomes turbulent, greater the resistance. So the faster you're going above 55 miles an hour, the worse your gas mileage becomes. Here's the drag force on an object. 1/2 rho is the density of the fluid through which you're going, and the drag force depends on the square of your speed. So if you go twice as fast, the drag force is 4 times as great. This is the drag coefficient, and A is the area of cross section perpendicular to the direction of travel. Okay. So turbulent flow is random and chaotic motion. When flow becomes turbulent, resistance increases and flow rate decreases. Okay. Now, Reynolds number is a number that tells you when turbulence will set in. Okay. The onset of turbulent flow is determined by a dimensionless number called the Reynolds number. So here's an object sitting in, let's say, a wind tunnel, and you can see that at low Reynolds number, below that Reynolds number, below this guy, the flow is laminar. And above this Reynolds number, flow becomes turbulent. Okay. And the drag, so for instance, if this was a object flying through air with turbulence, it's facing a far greater resistance than this guy would be facing. So the Reynolds number depends on the density of the fluids. So the Reynolds number depends on the density of the fluid through which you're traveling, and the diameter of the object, and the speed of the object, or the fluid if the fluid is going around it. So it's the relative speed and the viscosity of the fluid. Okay. Depending on the geometry, the onset of turbulent flow occurs when the Reynolds number is greater than about 2500. The boundary layer will transition from laminar to turbulent flow. So here was a laminar flow, and it transitioned to turbulent flow about a Reynolds number of 2500. Okay. Larger velocities, larger objects, and lower viscosities contribute to the larger Reynolds numbers. So lower viscosities contribute to larger Reynolds number. Okay, so lower the viscosity, higher the Reynolds number. Higher the diameter, higher the Reynolds number. Okay, so here's a pipe whose area is changing, and if there's no leaks, whatever fluid flows in has to flow out. So if 5 gallons a minute are flowing in, and 5 gallons a minute must flow out. Okay, in fact, at every location, 5 gallons a minute are flowing. Okay, so this fact is given by this equation. The flow rate is given by the area of cross section of the pipe times the speed at that point. Okay, so, and this is constant. So lower the area of cross section, faster the fluid flows. Okay, lower the area of cross section, faster. So the fluid is flowing much faster here, and here the area of cross section is larger and it's flowing slower. Okay. So Mr. Bernoulli gave us the principle. Pressure in a fluid varies as it moves through a region where speed and or elevation changes. So Bernoulli's principle states where the speed of a fluid is high, the internal pressure is low. And where the speed of a fluid is low, the pressure is high. So fast moving fluid has lower pressure, internal pressure. Okay. The relationship between fluid, speed, pressure, and elevation was first derived by Mr. Bernoulli. And here's Bernoulli's equation. Okay, so you see here's a pipe that's okay. Its speed changes with area of cross section. The speed of the fluid also changes with the height. Okay, so when you throw a ball up as the ball goes higher up, it slows down. So that changes the speed as well. And so, well, so when the fluid goes up, what happens is the pressure decreases. Yeah. All right. So what Mr. Bernoulli found was the pressure at any given location, and here is the kinetic energy per unit volume, and this is the potential energy per unit volume. So the sum of these three terms is constant. So the sum of those three terms is the same wherever you go in the fluid. Okay, and this is Bernoulli's equation. What we'll be mostly interested in is the following. Okay, so we'll mostly consider where the fluids are at the same level. And so let me write this. So P1 plus 1 half rho V1 square equal to P2 plus 1 half rho V2 square. Okay, so if a fluid is flowing faster, V2 is the speed. If it's flowing faster, if this term is higher, the pressure drops. Okay, so that's what you want to remember. The faster a fluid is flowing, the lower the pressure there. Okay, so if it's flowing fast there, the pressure there is lower. Anyway, so the sum of these two terms, as long as it's flowing in a in a level area, so the sum of these terms will be constant. Okay, so here's entrainment. So again, we're going to use this idea: faster fluid is flowing, lower the pressure. Okay, so for instance, in a Bunsen burner, here's natural gas that's blown in, and it's flowing fast, and you have a side opening. Air is at atmospheric pressure. In the flowing natural gas, the pressure is lower, so air will flow from a high pressure to the lower pressure, and air will get entrained in this thing, and then the mixture will burn. Without the air, the natural gas cannot burn. Okay, so we use that. In a perfume bottle, when you have a bulb that blows air across the tube, and when the air is flowing, the pressure here is decreased, and the atmospheric pressure and the pressure of this fluid will push the perfume up, and it gets entrained in the air column. Okay. So here's all right, so we use entrainment in quite a few applications. Whenever one fluid is inserted into the flow of another fluid, so air is inserted into the flow of natural gas, perfume is inserted into the flow of air. One fluid is pushed into the other because the pressure in the rapidly moving fluid is smaller than the outside pressure. The fluids involved in entrainment may be liquids or gases. Many entrainment devices have a jet or constriction designed to increase the speed of fluid and enhance entrainment of another fluid. Automobile carburetors entrain gasoline into an air in a venturi. So these guys know Bernoulli's effect as well. So when they build their underground tunnels, one of the openings is higher than the other opening. And across the wind blows faster as you go higher up. Okay, so the wind here across this hole is faster than this wind. Faster wind leads to lower pressure, and the pressure is higher, and so now you have an air conditioning system. The higher pressure blows air through their tunnel like that. So these guys are quite smart. So you have higher pressure here, and that blows the air like that. Now we'll talk about cohesion and adhesion. Cohesion is attractive forces between like molecules, and adhesion is attractive forces between different molecules. So let's say if you have water water in a glass, the attractive force between water molecules is called cohesion, and the force between the water molecules and the glass is called adhesion. Okay. So forces between molecules can be either attractive or repulsive. So even so even if so you take two water molecules, and so what this graph is telling you is that's the potential energy, and if the water molecules are this further than this far apart, the force is attractive. So if you have the water molecules that are greater than a certain distance, there'll be attractive force. But if you bring the water molecules too close, they want to repel each other. Okay, so they don't want to be closer than a certain distance. So if these molecules are closer than this distance, then the force becomes repulsive. Okay, but we are going to mostly talk about the uh, attractive region. Okay. Cohesion is between attract forces between like molecules, and adhesion is between unlike molecules. Okay. So we are going to talk about the attractive part of the force. The attractive part of the force is responsible for numerous phenomena, among which are surface tension, capillary action, and fluid viscosity. Attractive forces between molecules of the same type are called cohesive forces. Those between dissimilar molecules are called adhesive forces. Okay, so this is like molecules and unlike molecules. Okay, so the cohesive force between water molecules is what makes this possible. See, so the surface of a lake, let's say, or a body of water is like a stretched rubber sheet, and you see, and these as long as you don't break the surface, this this bug is being supported by the surface of the water. You can even make a safety clip float on the surface of a water. What to be able to do this, what you have to do is you have to place it gently without breaking the surface of the water, and you can do this at home. So the liquid surface acts like a stretched rubber sheet that tries to contract and make the surface area as small as possible, hence forming. Okay, cohesive force in liquids cause them to beat up as in raindrops. Okay. And so to minimize energy, you want to minimize the surface area. So the liquid surface acts like a stretched rubber sheet that tries to contract and make the surface area as small as possible, and forming beads. The surface is under tension, and overall effect is called surface tension. Okay. So here's how you measure surface tension. And so if you want to measure the surface tension of a soapy water, this is this device is made out of wire. Get your film on there, a soapy film, and then you pull on that. And every film has two surfaces, so the force we are talking about is force per surface. Anyway, you apply a force and pull on this. Okay. And the surface tension is the force you have to apply divided by the length of this wire. So force per unit length you have to apply. Okay. And you see for mercury, it's enormous compared to these guys. And for blood plasma, it's 0.073 Newton per meter. That's the surface tension is denoted by gamma. It's 0.073 Newton per meter. So what that means is, Newton is, I'm going to give you an equivalent in grams. Okay, if you divide by G, that's 10. So that would correspond to 0.0073 kilograms, which is 7 grams. Okay, so what that number tells you, what that tells you is a meter long. If you made a film of blood plasma a meter long, you would have to apply a force of 7 grams to move this movable wire. So that's the kind of force you would need to apply. And you need to apply that force because the blood molecules are attracting each other and they want to minimize the surface. Okay. See, mercury has a very large surface tension. So anytime you might have seen when a thermometer breaks and a mercury spills, all the beads are tiny and and so on. Okay. So here's water. The surface tension of water is 0.076. Soapy water, the surface tension is lower, is about half. So any substance that decreases the surface tension is called a surfactant, and this will become important. This concept will be important. So surfactant are substances that make the surface tension of a liquid, lowers the surface tension of a liquid. Okay, so surface tension is denoted by gamma, and it's the force per unit length. All right, go watch this video. Okay, so in this diagram, what we do is, okay, so if you have a balloon, what the balloon does is, because the balloon is a stretchy surface, it increases the pressure inside the balloon. Okay, so surface tension causes balloons as well as droplets. The inward force of the surface tension, the inward force makes the bubbles spherical and raises the pressure of the gas inside. So it raises the pressure. The extra pressure is given by this formula. Okay, so the extra pressure, okay, so for a balloon to stay, okay, so there's atmospheric pressure, and the balloon is exerting a force, so the air inside has to be at a higher pressure, and the extra pressure is given by this expression. It's 4 gamma. Gamma is the surface tension of the material. In this case, it would correspond to the balloon, the tension of the balloon, and divided by the radius. So smaller the radius, higher the extra pressure. So when you first see this, you would think that air would move from here to there, but smaller the radius, higher the pressure. Smaller the radius, higher the pressure. And so this air is at higher pressure than this, and air will go from here to there. All right, so that's one of the reasons. Well, you have tiny alveoli in your lungs because you're exchanging gases via diffusion, and you learn in the next chapter, molecules don't travel too far during diffusion, so your alveoli are tiny, and you can think of that as outside air, and so the higher pressure, and there's other elements to it, the higher pressure will help you exhale air. Okay, so smaller the bubble, higher the pressure. The process is crucial to normal exhalation and breathing. Adult lungs contain about 300 million tiny mucus-lined sacs called alveoli. Okay. And so you'll see also, here's another problem. If the surface tension is too high, the pressure is too high, then it's hard to inflate the alveoli. Okay, and there are some newborns have that problem where the surface tension is too high, the pressure inside is too high, and so it collapses, and the atmosphere, you're not able to inhale, or this is not able to expand, and you have a hard time breathing. Okay, and so you would need surfactants to reduce the surface tension. Okay, but anyway, we'll come to that. Okay, so adult lungs contain about 300 million tiny mucus-lined sacs called alveoli. The exchange of gases, so they have to be tiny because gases are being exchanged via diffusion, and exchange of gases such as carbon dioxide and oxygen with blood occurs in these sacs. The large number of sacs increases the surface area available for interchange. When a person exhales, the alveoli contract under the effect of surface tension in the mucus lining. Pressure created, so when you want exhale, you want the pressure here to be higher than the pressure, atmospheric pressure. And so the pressure has to be higher than the atmospheric pressure and air will go out. And we'll come to that next chapter. Okay, so when a person exhales, the alveoli contract under the effect of surface tension in the mucus lining. Pressure created in the alveoli, but the surface tension is largely responsible for exhalation. And then also in the tracheal cavity also, we'll come to that as well. It helps to create a larger than atmospheric pressure in the lungs. So you have to have larger than atmospheric pressure in the alveoli or in the lungs for the air to move out into the atmosphere. Sometimes surface tension in the alveoli can also be too large. So if this guy is too large and the pressure is too large, then you can't even breathe and inflate the alveoli. Surface tension in the alveoli can be too large, making them very difficult to inflate, meaning you're not able to breathe. Such a problem, called respiratory distress syndrome, occurs in premature infants and can be fatal. Normally a substance called a surfactant that reduces the surface tension of the mucus lining of the alveoli so that they can be inflated properly. Some infants lack surfactants and can only breathe with great effort. So if they lack surfactants through some genetic defect, then they have trouble breathing. A similar problem occurs in drowning victims. Expelling water from the lungs only partially restores the ability to breathe, since the water increases surface tension in the alveoli, making them difficult to inflate. Okay. So a surfactant or a surface active agent is a substance that lowers the surface tension of a liquid. Yeah. So that's what a surfactant does. So here are a couple of other diseases or problems. Okay, so here is alveoli, and the importance of surface tension in the lungs is seen in victims of emphysema. Okay, so again, the pressure, so here was the expression for pressure. Pressure was 4 gamma divided by R. Okay, gamma is the surface tension, R is the radius. Again, there's that expression. Okay, what happens in the case of emphysema patients is some of the alveoli coalesce and become larger. When they become larger, the radius increases, the pressure inside them decreases, and so the pressure is not as high, and they have trouble expelling the air from the inside to the outside. Okay, so that's the problem when the radius increases. Okay. So the importance of surface tension in the lungs is seen in victims of emphysema. Several alveoli coalesce in the people suffering from emphysema to form fewer but larger alveoli. Radius increases. The effect of the large sac is a reduction in pressure because of their larger radii. When a person with emphysema attempts to exhale, his alveoli create a small pressure and airflow is less than normal. The lungs have effectively lost some of their elasticity. Okay, so that's what's happened. And in addition, from a larger sac, it's harder to exchange gases, so it's a double whammy. You can't expel air, and you're not efficiently exchanging air as well. So this problem illustrates all that. So it shows you, so it considers it's doing it with water, but the point is the same. Okay, so it considers the water bubble 2 × 10⁻² 2 centimeters. 10 to the minus 2 centimeters. 10 to the minus 1 centimeter is a millimeter, so this is a tenth of a millimeter. And then here's a bubble that's 5 times larger. And then we'll consider the same bubble size, but with the surfactants and the reduction of surface tension to 0.037. Okay, so again, here's the pressure is 4 gamma divided by R. Oops. So let me write this R differently. Okay, R. Okay, so in this problem, we're going to consider different radii and then reduce the surface tension, okay, and calculate the excess pressure inside the bubble. So there's the first case, and there is the surface tension for normal water without the surfactant, and this is for the first case. So it goes through the problem. The excess pressure corresponds to 10.8 millimeters of mercury. When the radius is 5 times greater, the pressure decreases. So essentially it becomes 10.8 divided by 5. So it's 2.16 millimeters of mercury. So in the case of emphysema patients, the radius increases, and you see the pressure inside the alveoli is small, and so they're unable to expel the air to the outside. Okay. And we'll come to that. We will need to know the pressure inside your trunk cavity. So we'll come to that in the next chapter. And in this part, again, your radius is the same, except you're decreasing the surface tension by a factor of half. And so here's the surface tension, and so you work it out, and that works out to 5.5 millimeters of mercury. So the excess pressure is 5.5. Okay, and this is just right. Okay, so for instance, in a drowning patient, when it's the water mixes with mucus, the pressure is too high. So even though you remove water, it's hard to inflate the alveoli. This is for the emphysema patients. The pressure is too low, and this pressure is just right. So with surfactant added to the mucus, the surface tension decreases, and this pressure is just right to breathe. Okay, so the bubbles in this example are similar in size to the alveoli. In fact, in the first case, the pressure is a bit high for easy inflation of the alveoli. So at that pressure, it's hard to breathe in alveolus, whereas in the second case, it's a bit low to cause normal exhalation. In the third is just about right, I guess. So, yeah, so it's an illustrative problem. So adhesive forces vary in strength. Adhesive forces are forces between unlike molecules. Okay, so you see when the adhesive forces are great, then the liquid will wet the surface. When adhesive forces are smaller, so when cohesive forces are greater than adhesive forces, you have beads forming. So this is water on a waxed surface, and this is water on an unwaxed surface. Okay. So there's the difference. Water adheres well to glass and rather poorly to wax. So the strength of adhesive forces has a visible effect on how a liquid wets a surface. If the adhesion between the liquid and the surface is strong, the liquid will wet the surface easily. Okay. High surface tension in the liquid tends to inhibit the wetting process. High surface tension corresponds to high cohesive forces, since there's a strong tendency to form drops instead. Water has a relatively large surface tension and does not easily wet many substances, such as polyester fabric. Soap A surfactant reduces the surface tension of water, allowing it to penetrate and wash away particles of dirt much more effectively than plain water. So soap is a surfactant. So now we'll talk about capillary action. You see, here's a dish containing water, and if you use capillary tubes, thinner the tube, water rises. Water rises in this tube, and you do the same experiment with mercury, and mercury decreases. It turns out that for water, the adhesive forces are large compared to the cohesive forces, and for mercury, the cohesive forces are much larger than the adhesive forces. Okay, that's why so capillary action is the rise or fall of a liquid in a tube owing to the interplay of cohesion and of the liquid to itself and its adhesion to the walls of the tube. So it's interplay of those two forces. If the tube diameter is larger than 0.5 centimeters, the rise is negligible or the depression is negligible. Okay. So the smaller the diameter, the higher the water rises. Thinner the tube, higher the water rises. So shown are glass tubes inserted in water and mercury. So water is raised and mercury is depressed by capillary action. Okay, and here's the meniscus. Okay, so the meniscus of water is curved upward while that of mercury is curved downward. Mercury has a high surface tension, mercury has high cohesive forces and forms a surface curved downwards like a drop. Adhesive forces between mercury and glass are weak compared to the cohesive forces in mercury. So in mercury, cohesive forces are larger than adhesive forces. Water has both smaller cohesive forces and much larger adhesion to glass. So in the water, it's the opposite, and the meniscus is like that. In the water-filled tube, the adhesive forces are stronger than the cohesive forces and pull the water up the walls of the tube, and this is important. This is part of how water rises up in plants, and so that's why we're looking at this. So capillary action, the height to which capillary action can raise or depress a liquid in a tube depends on several factors. The height is proportional to surface tension, inversely proportional to the density of the fluid, and the radius. Smaller the radius of the tube, the more molecules are in contact with the sides of the tube, and less mass there is to be raised. So you have to raise less mass. So narrower the tube, higher the liquid will rise. Denser the fluid is, more mass is to raise, and the height is inversely proportional to the density. Okay. Anyway, narrower the tube, higher it'll rise. Okay. Heavier the liquid, less it'll rise, and so on. So, okay. So the question of how tall trees raise sap to their uppermost branches is a controversial one. Veins in trees are not small enough to raise sap more than about 10 meters. And there are trees that are over 100 meters tall. Okay. So osmosis produces root pressure, which can also be shown to be inadequate to force sap to the top of tall trees. Okay, we'll learn about osmosis next chapter. The actual mechanism of how the tall trees get their water all the way to the top is not well established, but one possibility is that the sap is raised in stages by capillary action. Okay, so you raise the water in stages. It's also been suggested that cohesive forces pull sap up in a long chain. So this idea is that the water molecules are attracted and they form a chain. And when this molecule evaporates, this molecule comes up, and so on. Okay. As one molecule evaporates during transpiration, another is pulled up by the cohesive forces in the chain. Okay. Pulling is opposite of pushing, which is what positive pressure does. Pulling thus corresponds to negative pressure, absolute pressure. So essentially, do the channels, the water channels in plants, do they have negative pressures? Some researchers have reported negative pressure as large as minus 25 atmosphere. That's a huge number in the sap at top of trees. Okay. Okay, so with that, 1 atmosphere corresponds to 10 meters. So with that kind of pressure, negative pressure, you could raise water up to 250 meters. Okay. But so anyway, it has not been possible to recreate sap behavior under laboratory conditions. So in a lab, we haven't been able to raise waters as far as high as some of the tall trees, or to understand the phenomenon theoretically. The question remains open and under active discussion. All right, so we studied capillary effect, and one of the things we would try to explain was one of the things we are interested in explaining is how water rises in trees. Okay, and again, it's an question that has not been settled properly. Okay, so that ends this chapter, and we'll see some of the application of some of the concepts we've learned in the next chapter. Okay, that's it for this chapter.